Okay, so let me start by declaring my goals for today. Today I have two major goals. The first goal is to define and describe some properties of the algebra of symmetric functions, which I haven't done yet. And the second goal is to start our discussion of RSK algorithm. So for symmetric functions, it will be mostly without proofs. So I did try to prove something for symmetric polynomials yesterday. For symmetric functions, so I will need some facts about symmetric functions, which I will just state and will not prove. But first of all, let me first recall Cauchy identity. So a couple of facts about symmetric polynomials. So Cauchy identity says that when we sum over all lambda of a Young diagrams, products of Schur functions, we obtain very nice and simple product expression. So I will prove it either today or next time with the use of RSK algorithm. So as for now, this is just some fact that I need to define Schur measure. But I also need, so for defining the Schur process, I also need one more symmetric polynomial, which is called skew, Cauchy skew Schur functions. So it takes two Young diagrams, and by definition, this is a polynomial and some variables x1, x, and minus k. It will be more convenient to write in this fashion. So it is a sum over certain Young diagrams such that lambda, such that mu, which is equal to lambda k, interlaces with lambda k plus 1, interlaces with lambda n, which is lambda. And the sum is the same as in the combinatorial formula for Schur functions. So I need to write x1 to the power lambda k plus 1 minus lambda k x n minus k lambda n minus lambda n minus 1. So for combinatorial formula for Schur functions, I recall that we had a sum of all interlacing arrays. So we had fixed top level lambda, and then we summed over all interlacing arrays, and then we took a very similar expression. And this was like an equivalent definition of a Schur function. So now for skew Schur function, we need to fix like a section. So we also need to fix bottom level and do the same summation. So this is obviously a generalization of Schur function. If we take mu is an empty set, we obtain just a usual Schur polynomial. Yeah, so this is polynomial. That's for now. Combinatorial formula is very similar, but we do not have any determinantal formula for this thing. So any similar nice determinantal formula for this skew-Schur function. But combinatorially, we need this object because we want to, well, to study combinatorial properties, and it will be important for us. So like an immediate corollary of such a definition is that if we sum over all mu Schur function one set of variable and then multiplied by Schur function, this skew-Schur function, so what we will obtain if we do this summation of all Young diagrams? Yeah, that's lambda. So we have this section. So if we add like some vertices here, then it will be like full interlacing array, and this will be just combinatorial formula for S lambda in the set of variables y1, yk, x1, x, and minus k. So this is like quite nice objects, Schur functions, and like knowing this and knowing this, we can say something about this skew-Schur function as well. So we have this combinatorial identity. Well, that's all that I wanted to say about polynomials today. Now let us go on to symmetric functions. Yes, yes, yes. So if we take Schur polynomial, we take two sets of variables, and then we are asked what is the coefficient of like this set of variables. So this is obviously just a characterization of Schur function. Thank you. Yeah. So the idea is to consider these polynomials in infinite amount of variables. So why do we need this? Well, so we need this for so this is not like a big change. This is just like some small technical step, and we need it because basically these objects work nice when we have very large amount of variables. So definition of any like Schur polynomial or like any other polynomials that we have, it breaks if the number of variables is too small. So for example, if we consider something like elementary symmetric function, if we have not enough variables, then we will enlarge Young diagram to not enough variables, then it will be like something like 0. So we have like some problems with defining this object. So it's convenient to consider these polynomials in infinite amount of variables, and formally this can be done in the following way. So let us consider symmetric polynomials in x1, xn. So this is symmetric polynomials in x1, xn of degree small n. So this is a homogeneous polynomials of degree small n. Now there is a very easy map from the space of polynomials in n+1 variables to the space of polynomials of n variables, which set x n+1 to 0. So we just forget about one variable. And now, by definition, symmetric functions, not polynomials, but functions of degree n is the sequences of polynomials such that Fn belongs to so Fn is a symmetric polynomial in capital N variables, and it works nice with these projections. So if we take projection of n plus first element, this will be an element for any n. So this is a little bit probably confusing, because this is a very, very easy step. So we just consider the same polynomials with the same definitions, just in an infinite amount of variables. And like this transition, so one can say that this is projective limit in the category of graded rings or something like this. But we don't need this. So this is just basically the same polynomial, which is stable when we set one variable to 0. So it's much easier to think about this in this term. And then algebra of symmetric functions. Is well, just a sum of all these homogeneous components. Let us have some examples just to better understand this definition. So for example, sum of xi squared when I ranged from 1 to infinity. Does it belong to this symmetric functions algebra? Yes. So when we set 0, so as this set Fn, we understand this as a sum from 1 to n, and then it satisfies these stability properties. So it's just convenient to write this as a sum of infinite amount of variables. Yeah. Yeah. So homogeneous. Yeah. I agree that I should write this homogeneous. Yeah, so this is just like, so we have like 1. We have element 1. Yeah, so this is like unital algebra. So this thing does belong to symmetric algebra. So what is slightly confusing, this thing does not belong to this algebra. So this thing satisfies the stability condition. If we set some variable to 0, we just obtain the expression of like in a small amount of variables. But we want this function to be of bounded degree. So by definition, we just want to consider polynomials of bounded degree. And the degree of this polynomial grows as the amount of variables grows. So it doesn't fall into this definition. So still it looks like it might be here, but it's not. And more generally, so some questions about this definition of these symmetric functions. This is just a technical definition that we need, and it's quite convenient just to think about them as polynomials in infinite amount of variables of bounded degree. So now I want to state some properties. So any questions? So I want to state some properties of this algebra. So we had several families of symmetric polynomials. So first claim is that all our polynomials also produce symmetric functions. So for any lambda, L and mu, m lambda, e lambda, h lambda, what others do we have? P lambda, S lambda, and also today we had S lambda mu are symmetric functions. Formally, I need to write these symmetric functions as this series of polynomials. So I had this definition for each n. So I can write this like e lambda of x1, xn, e lambda of x1, xn plus 1, etc., etc. So formally, this is like this object. But really, this is just a sum of like a polynomial in infinite amount of variables. And we can, so for these things, we can just check from definition if we plug one variable to 0, then we obtain the same object of like smaller size. And for this thing, stability follows from combinatorial formula, for example. So lambda and mu from Young diagrams. So we have some examples of these symmetric functions. So how to understand the whole algebra of symmetric functions? So this will be just a fact. I am not going to prove it. So fact that each of the following collections, m lambda, e lambda, so I'm not lazy, I will write all of them once more. P lambda, and Schur functions S lambda, form a linear basis in symmetric functions. So what does it mean that we form a linear basis? That means that every element or every symmetric function is just a finite linear combination of, like, so if I take, for example, monomial functions, I can just need to take some finitely many. So there is no limit here, so it's important. So that's why we excluded this example. So we want to have just finitely many terms in this sum. This is just like a known as linear basis. This is just finite linear combinations of any of these functions. So for monomial functions, it's more or less a definition, this statement that this is a basis. For other examples, elementary, complete, power sums, Schur functions, so this is a certain statement that needs to be proved. For us, it will be just a fact that like any of these functions work and any of this function. So there are two statements here. First, that they are linearly independent in the algebra of symmetric functions. This is not true if, so we consider all Young diagrams, and if we take just finitely many amount of variables, they will be linearly dependent, of course. But since we take already take this limit, we take infinite amount of variables, they become linearly independent, and every symmetric function can be expressed through them in a unique way. Yeah, so we think about so the field can be taken like in different ways, but we think about real coefficients here. Questions? Yeah, so this is some understanding what objects do we have in this symmetric function. So for example, we can take, and we will take, so for example, Newton power sums. So we have pk So as a part of this fact, we know that this family is algebraically independent. Because, well, P lambda is just a product of pk's, and if we don't have like any linear dependence between P lambdas, that means that we don't have any algebraic dependence for pk. So we just have some P1, P2, P3, these like objects, our generators, then we can multiply them, sum them, and obtain all elements of symmetric functions. So this is how we can think about algebra of symmetric functions. So now my next goal is to define the notion of specialization. Specialization of the algebra of symmetric functions is algebra homomorphism from this algebra to real numbers. So we take this algebra and send it to real numbers. So how we can think about this? We can think about this that we send somewhere functions Newton power sums. We can send it in like arbitrary real number because they are algebraically independent. And then if we know the image of this family, then we automatically know the image of every other symmetric function. So like we can think about at least, well, for power sums, but we can do this for EK if you want. So this is how we can think about the specialization. So as for now, this is just a pure algebra. But at the end, I want to define a Schur measure for this. So this is a probabilistic object. So probability should appear at some point. So probability measure is a very simple thing. For probability measure, we need a collection of reals that are summed up to 1. This is one condition. But unfortunately, we need another condition that these reals should be non-negative. Otherwise, it's a different object. We then don't have probabilistic intuition about it. So as I said in the previous lecture, Schur measure comes from Cauchy identity. So Cauchy identity supplies us the collection of reals which are summed up to 1 and which are indexed by Young diagrams. But we also need these reals to be positive. And more general condition is that the specialization of algebra of symmetric functions should be Schur positive. So let me write this formally. Specialization is called Schur positive if for any lambda, so specialization phi, for any lambda we have phi of S lambda is greater than 0. So this is some fairly non-trivial property. Because, well, so we can send pk to anywhere, to any real numbers, but there is no guarantee that we obtain something positive here. So we have infinitely many inequalities of this sort. So we need just some general method how to understand whether this specialization, if we send it like to some, just to some reals, and then we need to check whether this infinite amount of inequalities hold or not. But we at least know about one example, so one family of examples of such specializations, so probably some ideas. So just to name some specializations where we do have this condition. So, but we cannot send all S lambdas, they are algebraically dependent. So yes, that's of course true. Yeah, so if we have these variables x1, x2, xk, and so we can recall this structure of Schur polynomials and think about this not like elements of some symmetric functions, but send these xi to somewhere. So this is called, probably slightly unofficially, example 1, alpha specialization. So in terms of pk, so we can send pk's anywhere. So let us send every pk. So let us fix some positive reals a1, a2, an, and send pk to a1 to the power k plus an to the power k. So this is exactly the value of a Newton power sum on these variables. So why this specialization is Schur positive? Yes, okay. So if we have, we have combinatorial formula for Schur functions. So if we have, if like all participating variables are positive, then we have something positive as a result. So combinatorial definition gives us this positivity for every lambda. A1, AN is greater than 0. By combinatorial formula. So this is this example 1 is our previous situation. So for this example, we didn't need to come to Schur functions. We just can do all things with Schur polynomials. And this is still quite reasonable, of course, and this is an important specialization as well. Yeah? Yeah. So we fix like find many reals and then send pk to this thing, which means that other variables are automatically sent to 0. So this example we have for Schur polynomials. But the point is that we have a little bit more on the level of Schur functions. So this will be like fact. So it's typically referred to as Thomas theorem. So it's in different versions. It's also due to Edray and probably Vershik-Kerov about the first. Who wrote this in this way. Probably all of them should be mentioned. So like the complete classification of Schur positive specializations. So this is just some example, but we have a little bit more. So complete classification is the following one. So let us find infinitely many alpha variables. Fix infinitely many beta variables. We have something new. So alpha will play this role, but betas will be something new. And also let us fix one real variable gamma, which is also non-negative. And our conditions on them is that sum of alpha i's plus beta i's. So the sum should be convergent. So it can be infinite. So there can be infinitely many terms, but the sum should be finite. So these are our parameters of our specialization. And then send, so for example, I took pk here, so let us describe specialization p alpha I, beta j, gamma by sending the generator pk to, so I need to have this term, sum alpha I to the power of k. Then I have something slightly different here. Okay. And, well, I will write it in a compact way, so it will be plus gamma in the case if k equals 1. Yes, that's true, but well, it's just more, okay, yeah, I can't do this. So I can also not put alpha 1, for example, here. Okay. So I defined the family of specializations in this complicated way, and the statement is that . all this specialization for arbitrary choice of parameters are Schur positive, and this is a complete list. So which means that any Schur positive specialization must have some parameters alpha i's and beta j's and gamma in such a way that pk is sent to this quantity. Yep. Yes, exactly. Yeah. So it implies because, well, so all these alpha i's and beta i's are less than 1 from some point. No, I don't assume. That means this like from calculus. So like if we have convergent sum, then from some point it's less than 1, the terms. So if we raise to the power k, now a real which is less than 1, then we obtain something smaller. Yeah, so but this is a like very good question. So indeed, so this condition implies that all images are finite. So this is like nothing is divergent here. Yeah. So first of all, we need to be. There is also like condition of homomorphism. We cannot send like S lambda because S lambdas are algebraically dependent. So we can send pk. So k is like an integer. So they are algebraically independent. We can send them anywhere. But S lambda, they are linearly independent, but algebraically they are dependent. So we cannot send like all S lambdas to something. This is like just a definition of a homomorphism. So it should behave good when we have a summation and multiplication. So we cannot send, for example, all p lambdas to something that we choose. No, we can send only pk's, and then everything else is determined. And for S lambda, we don't have like this algebraically independent family. So we have it for p lambda, h lambda, and e lambda. Other questions? So this is a like important theorem, which I'm not going to prove. Yeah, so in the definition of these three families, we first define something like pk, ek, or hk, and then p lambda is just defined as a product of pk's. So this is not the case of S lambdas and M lambdas. So they were defined like directly for arbitrary Young diagram. So if we were, so this statement, this fact, claims that these things are linearly independent, which implies that pk, not p lambdas, but pk's, are algebraically independent. Yeah. So I think it's like, so I gave yeah, so I think like this is like so I gave this reference for Macdonald's book. It's basically there, but probably not like not the proof, but okay. So at least this is like a good reference for symmetric functions. As for the proof of this theorem is, so there is a recent Borodin-Olshansky book, which like gives the proof of this theorem in great detail. And frankly speaking, probably there are more references. I just so this is Borodin-Olshansky book. Probably it's 2016, very recent. And probably there are more references, I'm just not sure right now. So what are the other references? Questions? Yeah, so this is like really close, and we try to do different stuff, yeah. So it's easy to check, and it's written basically in Macdonald's book, that these things are Schur positive. So this part is like quite easy. The part that this is complete classification, this is a complicated fact, and well, it requires, so there are like several proofs, but it requires, well, some methods, like some serious methods. It's cannot be done like in 5 minutes, like even ideas. So there are like different ideas. So the idea of Versche-Kerr was to use some idea from ergodic theory. Thomas originally encountered these problems for like an infinite symmetric group, and so he used some methods from complex analysis. So some tools are needed for the proof of the statement this is a complete classification.
I cannot reproduce it without.
I think multiplication with determinants is about part that this list is Schur, so that they are Schur positive.
Oh no, that was converse.
Well, I don't know. Probably, I don't know about this. Yes. Yeah, exactly. Yeah, so it's very yeah. So this is a moment of a measure with atoms at alpha i's, atoms at minus beta i's, and also with atom at 0 of size gamma. So this is a very good way to think about this formula, yes. Well, as I said, so I just keep a lot of material in, and I will not prove this. Okay, so this is Schur positive classifications, and finally, I can give like quite general definition of a Schur measure. Or should I discuss beta specialization first? Okay, let me discuss beta specialization first. So we have two new objects here. We have betas. So example 1 was about alphas. We have betas and gamma. So in general situation, they are mixed, so we can have some alphas, some betas, and also gamma. But let us think what happens if we have just betas. Probably not think, but just state so if we have finitely many, just for convenience, reals beta 1, beta n, then so we know what happens with pk, but also I can just claim what happens with other functions, phi beta 1 beta n of S lambda. So this will be the most important example for us. This is S lambda prime of beta 1 beta n, where lambda prime transposition So this is a certain non-trivial statement that if we apply beta specialization, which is defined by these pKs, then we obtain, so we apply this specialization to Schur function, we obtain Schur function, but with transposed Young diagram. So this is just a fact, and also let me write what happens when I apply beta specialization to an elementary symmetric function, then I obtain complete symmetric function evaluated at beta 1, beta n. And applied to complete symmetric function, I claim that I will obtain elementary symmetric function computed at beta 1, beta n. So these are some non-trivial statements about the algebra of symmetric functions. We can just believe in them, or I can read it in Macdonald's book. So they're mostly based on the fact that there is, that's a remark, that there is an involution in algebra of symmetric functions, which sends Schur functions to transposed Schur functions. So that's what happens for beta specialization. So we see that this is also like quite close to example 1. So, but we have this minus here, which leads that we need to relate not exactly these functions, but something which is closely related to these functions. And about gamma, I will not say much. I'll just probably say that it can be obtained as a certain degeneration. So it's not even an example. Let me say that this is an example. So if we understand this like our most basic specialization into alpha variables, then we can obtain something about gamma if we take alpha 1 equals to alpha 2, alpha n, let us say gamma over n, and consider n tends to infinity limit.
If I'm understanding correctly, this beta specialization is all our alphas are 0.
So I don't. So what is the question?
Do you arrive at these specializations by considering alphas are all 0?
Yeah, so I consider, so in example 2, I consider some special example of this specialization. So this is like complete classification. I take all alpha zeros, all the gamma 0, and take finitely many betas. And just state what are the properties of this specialization. So these statements are not hard, and like these properties can be proved, but I will not do this. Just to understand so what is happening here. So here we have just evaluations of symmetric polynomials, and here we have almost the same evaluations of symmetric polynomials, but slightly different symmetric polynomials. So here we need to evaluate transposed Schur function in the transposed diagram, and here we need to take interchange E lambda and H lambda. And also example 3, I also like to say something about gamma. So how can we think about gamma if we consider a lot of alpha variables of size gamma over n and take n tends to infinity limit, then P1, the sum of all alphas, will tend to gamma, and all other pk's will tend to 0 for k greater than 2. Yes, that's true. So if we are able to say something about this specialization, then taking this limit, so we also can say something about this gamma specialization, which is called Poincaré specialization, and which is well, very interesting and has interesting applications as well. So we have like 3 opportunities, alphas, betas, and gammas, which fall into this setting of Schur functions. And I try to describe what happens like in pure cases when we have pure alphas, pure betas, and a little bit about gamma, pure gamma. So all alphas and all betas are 0, and if we have some gamma, then we have some description of this situation as well. Questions? So probably I also recall that we had dominant tilings of Aztec diamond, and we had there like 2 combinatorial relations, interlacing in terms of rows and interlacing in terms of columns. Quite interestingly, we see that we have transposition here, and this transposition exactly has this effect. So horizontal interlacing becomes vertical interlacing. So that's basically the reason why we consider symmetric functions. Because in this generality, we can define a Schur measure which covers the case of Aztec diamond. So definition, which is due to Okounkov. Let A and B Schur positive specializations of algebra of symmetric function. Probability measure on the set of whole Young diagrams is called Schur measure. If probability of diagram is proportional to Schur function evaluated at first specialization times the same Schur functions evaluated in the second specialization. So I'm not writing normalizing constant here. So for this measure, so in order to have some normalizing kind of constant, I need to have some conditions on A and B actually. So let us do this probably later in the course when we will analyze asymptotic behavior of this measure. But we already have like some specific example if both A and B are alpha specializations into finitely many variables. Then we arrive at the definition of Schur measure for like our first version of Schur measure that I tried to define yesterday. But also we can now take like beta specializations here. Yeah. Yeah, so for some Schur positive specializations. So I don't want like to state explicitly now. So there are some conditions on alphas and betas such that the sum will converge, just converge. But well, just some examples. If we have finitely many alphas or betas, the sum will definitely converge. And yeah, that's enough for now. So we have some examples of Schur measures. So basically, because we have like Cauchy identity which nicely behave for products of two, but if we take one, it will be also like so we can also deal with this object. So this one is just well, more general. So we have more control. We have more control. We have two specializations. Then we don't have Cauchy identities. It will be nice to do something with this, but. Like Cauchy identity is like an essential thing here. So it means that there exists some finite real Z which may depend on A and B, but this is finite real, such that probability of lambda is equal to Z times the product of this specialization. Independent of lambda. Z does not depend on lambda, of course. Yeah, so it might depend on A and B, but do not depend on lambda. But also, I can now define Schur process, which is due to Akonkov Shetikhin. So if we have, so we need to think about these domino tilings and these conditions on signatures that we had. So probability measure on a sequence of Young diagrams okay, so let me is called a Schur process. If probability of configuration is proportional to so let me write a picture. So I will explain what is written here in the moment. So here we have two specialization as for Schur process. We can have like to n specializations. Lambda 1 E of rho 1 minus S lambda 1 minus rho 1 so I need to put here S lambda 1, yeah. Lambda 2 1 and finally in the end I will have evaluation specialization as lambda n. Well, for some full positive specializations rho 0 plus rho n minus 1 plus rho 1 minus rho n minus. So this should look scary. This will be especially scary if we didn't have an example of Artsec diamond, when we already had this sort of Young diagrams, which were related somehow. So in the example of Artsec diamond, we had these relations were interlacing conditions, and I will show in a moment how Artsec diamond fall into this general picture. But general situation here is that we can take arbitrary 2n Schur positive specializations, which, well, probably it's convenient to write them as like rho 0 plus, rho n minus 1 plus, and then rho 1 minus, rho n minus. And then we think about this picture, and we take S lambda 1, evaluate S lambda 1 at specialization rho 0 plus. Then we evaluate a skew Schur function lambda 1 minus mu 1 at specialization rho 1 minus. Then so here we have rho 1 plus, and to evaluate lambda 2 skew Schur functions lambda 2 mu 1 at this specialization. Yeah. Yeah. Yes. So we so probably it will be a little bit more clear when I say so in the case of Artsec diamond, it will be alpha and beta specializations. So this one will be alphas and this one will be betas, and this will lead to some combinatorial construction. But if we will take like all alphas, then this will be like some another construction. So I don't understand the questions.
Covering just needs to go into the so here you can add multiple boxes. You can add just from one time step to the other. You don't just add a single box.
So as for now, we don't have like any combinatorial structure here. So we will obtain it when we take the specialization something some specific specialization.
But could you enough just to have
No, it's not to have alpha and beta, but so the covering relations would correspond to your gamma speciality.
Yeah.
But that doesn't.
So what's the question? Yeah. So here it's phi, here it's rho. Here it's phi, and okay, so it's phi of rho. Well, it's not a convenient notation. I agree. Yeah, something happened.
What was called before alpha or beta?
So rho is a set. Okay.
Yeah, so rho is a set of alphas and betas and gamma. Okay, and okay. Yeah, thank you. It's rho is the set of alphas, betas, and gamma, generally. No. So we can take arbitrary alphas, betas, and gammas, and we will still obtain like a very analyzable picture. So the goal of this setting Schur measures and Schur processes. So it's quite a general definition, at least this one, but in this one as well, and like all probabilistic models which fall into this picture can be analyzed in very great details. So like this structure is very well analyzable, so to say. Yeah, questions? Okay, so let us have an example when we do have this structure. So proposition, nominal tilings of Aztec diamond form Schur process with rho I plus is equals alpha 1 equals 1, and that's all for any I from 0 to n minus 1, and rho I minus specialization into beta 1 equals 1, and all other variables are zeros for I from 1 to n. Yeah. So I'm writing only variables which are not equal to 0.
Okay.
So this is like the simplest specialization. So specialization when we have only one variable as something non-trivial, which is 1 here, and all other parameters are set to 0. So why do we have this? So in definition, we have like products of these Schur functions. So we need first to compute Schur function of in one variable. So so for alpha variable, so I take specialization into one variable and want to evaluate Schur functions lambda mu at this point. So what will be the result? So one alpha variable is 1, and all others are zeros. So for this object was defined as combinatorial formula. So this is So we have only one variable here. All others are 0. So we should. So here was like a sum of several variables. It was written in this place. And now, since we have only one variable, there should be only one variable present. Yes, the size of lambda minus mu is present in this formula, but well, we have this 1, so the size lambda minus mu was like in the power. So probably let me recall that S lambda mu, like pictorially, this is, so we need to sum. So we fix lambda here, we fix mu here, and we say, well, in general, we need to sum of some rows here, which is like an interlacing conditions between each two levels. But now we have only one variable. So one variable is 1, and all other variables are 0. So this is actually interlacing like this. There is no summation here. We can have only one level, lambda and mu. And only in this case, we can attain something non-zero. So I want to claim that this is like 1 to the power at lambda minus mu if mu interlaces lambda, and this is, of course, 1, and 0 otherwise. So let us probably as well some questions. So this is like so from definition of this Schur function. Yeah. So all the specializations are the same. They are specialized into one single alpha variable. So this is like a very easy situation when we have only one variable. We do not need to make any summations here. So this is like a specializations that kills almost everything. Questions? Yeah, this will be. So, but for now, this is just alpha specialization. Yeah. So this is. So we can have this picture. So we sum over all pictures when we define S lambda mu. We sum over all pictures, and we can have like at least some picture only if lambda interlaces with mu, and there is no summation here. So this is just 1. And for beta specialization, it's almost the same. But now for betas, so at least I claimed that all things are the same, but just we need to transpose all Young diagrams. So evaluation of beta variable will lead to the same formula. Probably I should write transposed here, but anyway, this is 1. In case when they are vertically, so if they differ by a vertical strip, and 0 otherwise. So this is probably let this be an exercise. So I understand that well, there are a lot of definitions. But from the facts that I claimed, this is like, I hope that this is quite visible, that if we believe in these facts about beta specializations and how it works, and also understand like the definition of Schur function, then just applying these two facts together, we can see that this gives rise to this object. And this was like a certain motivation why to do this. So of course, this definition is much more general. But in order to obtain Aztec diamond, we need both this and this. And now we have this in terms of beta variables and beta specializations. So if we know these evaluations, then probability of a sequence, so for Aztec diamond, for Schur process, probability of lambda i's, mu i's is equal to, well, it's not equal, it's proportional. So in the definition of Schur process, it's proportional to 1 if we have this combinatorial condition and 0 otherwise. So this is just a product. So this is definition of Schur process for these particular specializations. I need to take products of these ones subject to combinatorial constraints. And if I don't have combinatorial constraint, then immediately I will obtain 0. Yes, so this is a uniform distribution on signatures that have this combinatorial structure. And this is exactly domino tilings of Aztec diamond, which we saw yesterday. This is a uniformly random domino tiling. Some questions?
So you say that taking a uniform domino tiling as random is equivalent to random sequence and use?
Yeah, with these constraints. Yeah, so that's what we did yesterday. So there was like some combinatorial bijections. And then we see how these combinatorial constraints appear in the setting of Schur processes. So what is P? Yeah. Yeah, so if we take like, yeah, so it depends on, of course, on what measure we put on domino tiling. So if we put to horizontal dominoes like some different weight, it will be a Schur process. Probably this will be not one, but something else. So that's what I think. But for example, there is like an interesting situation when this is like a 2-periodic Aztec diamond, and this is not covered by this Schur process. So of course, it depends on what measure. So one can do something with this picture, but of course, it's not everything fall into this. All right, so at this point, okay, so I also probably should mention that you see that I didn't care about normalization constant here. So I could do this, so I can, so it's possible to write using Cauchy identities what is a normalization constant here. It will be some product. I did a very similar calculation yesterday when I computed the number of such signatures, and a similar computation is possible like in the general Schur process case, but probably it will be more natural to do later because well, one option was to start just from this definition and to describe how one can analyze global properties of Schur processes or local properties of Schur processes. So, like this result will give us a result about domino tilings as an application. So this theory is quite well developed, and it will be discussed late in this course. But the structure of this course that we want to start with all combinatorics. So I will continue with another combinatorial topic, and then asymptotic analysis of these Schur processes and some other models will be given later. So I will discuss a little bit more combinatorics, namely RSK algorithm. So RSK algorithm is some very well-established combinatorial topic. In particular, it could be understood, well, we can understand it as like a way to sample Schur processes or Schur measures. But of course, there are some other ways to sample these Schur processes. Still, RSK algorithm is quite distinguished because it gives us well, some quite rich combinatorial structure, and it's quite well developed in combinatorics papers. So let me probably be a little bit more specific. And so I am starting quite a new topic, but it's related to Schur processes, at least in the way that we will understand how to sample Schur processes and why this, better understand why these Schur processes are important, or why we have some other examples of interesting probabilistic questions that fall into formalism of Schur processes. So I started in quite a new topic, so probably like some questions about these definitions of Schur measures and Schur processes, which was like a main part of the first lecture and a half. Yes, so Polcherel measure is example of Schur measure when we take the specialization A and B like a pure gamma specializations. So we don't have alpha, we don't have alphas and betas. Alphas and betas are 0. We take some non-trivial gamma, and this will be, well, it will be what is called Poissonized Polcherel measure. It will be like almost Polcherel measure on partitions. Yeah. Yeah. So joint distribution is a Schur process. Yeah. So if we have Polcherel measures of well, so it's a measure, so there is some difference. So this is like a measure on the set of all Young diagrams. So not on the Young diagrams of size of fixed size, but on the set of all Young diagrams.
Okay, that's why you need to.
Yeah. So there is like a certain difference, but basically yes. So these situations falls into formalism of Schur processes. So one can extract results about Schur processes and then trying to prove them for Polcherel measures. Sorry?
So some step along the sequence.
So we want to define the probability measure of the whole sequence of Young diagrams. And this probability is proportional to a certain product. So product of two n terms. So for each specialization, we evaluate it at like a certain Schur function, which depends like on this picture. So generally, we evaluate like lambda I minus mu I and lambda I minus mu I minus 1. So the general terms in this product looks like this.
Okay. So what is my question? Yeah, what's inside prob is just a big sequence.
Yeah, so it's convenient to think about this sequence. And also, like Schur processes have many nice properties. So for example, if we have a Schur process and we fix And we ask about distribution of one particular diagram in this Schur process. This will be a Schur measure with some relation with what specializations give this Schur measure. Yeah, so and this is like a probability of like a distribution of the whole set, exactly. Yep. Yeah, so the sizes can be, so this is like some specific example for us, a diamond here. So we don't need this, so this is just some general Young diagrams, and like when we fix some specializations, that will give some conditions on them. Okay, so let us go to a new topic. Well, not, of course, it's very strongly related to this, and in particular, it will give us a proof of Cauchy identity. It will give us like a proof of certain skew Cauchy identities. But this is, well, quite another piece of combinatorics. So it's developed, so original paper, so RSK stands for Robinson, Schenstedt, and Knut. So Robinson-Schenstedt developed like an important part of the, a very important part of this algorithm, and then it was, this part was generalized by Knut, so it's natural to have like RSK.